Alright, we're going to continue some integration techniques, and again we're going to see some of the more difficult problems intertwined in these problems here. So on this one I'm going to start out by saying, well, I don't know the integral of tangent, so I'm going to rewrite this. I'm going to rewrite it as sine of 5 theta over cosine of 5 theta. What that does is allow me to go ahead and rewrite this as a u statement now, because if I take the derivative of cosine of 5 theta, I can get rid of the sine part. So I have negative 5 sine of 5 theta. That's my derivative, d theta. And then I'll rewrite this as 1 over u. This is my u. I need sine of 5 theta d theta. So I only need this portion, so I'll move my negative 5 to the other side by multiplying or dividing by negative 5. I'll plug a negative 1/5 and a du right here, so I can now integrate negative 1/5 ln absolute value of u plus c. So I have negative 1/5 ln absolute value of cosine of 5 theta plus c. In my next example, I'm going to do another u substitution. What I'm doing is I'm solving this differential, so I say dy is equal to 2x over x squared minus 9 dx. So I can now integrate both sides. My u is going to be x squared minus 9. My du ends up being 2x dx. If I integrate dy, I end up with y equals, on this right-hand side, I have 1 over u. I do need the 2x dx, so I'll just go ahead and write du. So y ends up equaling ln of absolute value of u plus c, and then I'll just substitute back my u in, so I get x squared minus 9. In the next problem, again, I'm going to solve the differential, so I'm going to solve for dy. So I end up with dy is equal to ln of x over x dx. Now I am supposed to find the exact answer on this, because they give me the particular. So I'm going to make my u statement be ln of x. I don't want to pick x, I want to pick ln of x, because when I take the derivative of ln of x, I get 1 over x dx, and that takes care of this 1 over x dx right here. So when I integrate both sides, I end up with y equals, and I'm going to rewrite this in terms of my u. I have u, and then I just need du to take care of the 1 over x dx. So I get y is equal to u squared over 2 plus c. So y is equal to 1/2. My u is ln of x squared plus c. Looking at this a little closer, I could actually bring this out front, and I'd get y is equal to just ln of x plus c. I'm going to bring this up top, and I'm going to plug in my x and y so I can find my c value. So I've got negative 2 equals ln of 1 plus c. The ln of 1 is 0. So I end up getting c is negative 2. So my final answer is going to be y equals the ln of x minus 2. Okay, moving on to this problem, we cannot make a u statement out of this. So what we're going to need to do is actually divide and use our long division. And you might be wondering how we're going to do that, but x times 1 gives me an x. So I'll just say 1 times x is x, and 1 times 1 is 1. And then I'll go ahead and subtract stuff off. And what I get is a 0, and I get a negative 1 minus 1, which is a negative 2. So I might actually be able to just say this is minus 2 over x plus 1. Now that does actually allow me to go ahead and integrate this at this point in time. So when I integrate, I get x minus this 2 just gets carried down, and it would be ln of absolute value of x plus 1. And I don't need to put plus c because I actually have a definite integral, and these directions are wrong up here. So I need to plug in 0 and 1. So when I plug in 1, I get 1 minus 2 ln of absolute value of 2 minus, plug in 0, I'd get 0 minus 2 ln of absolute value of 1. So when I simplify, I end up with 1 minus 2 ln of 2 plus 2 ln of 1, which is 0. So those fall out. And so my final answer is going to be 1 minus 2 ln of 2. My last two examples are much more easily done using second fundamental theorem of calculus. You can actually do it without using the second fundamental theorem of calculus, but they are much easier to use the second fundamental theorem of calculus, which just basically says take the derivative of both sides in terms of x. When you do that, these cancel, and you're left with the derivative equaling tangent of x. And it's that simple. If you'd like to see the other method of doing this in class and the longer method without the second fundamental theorem of calculus, I'll be happy to do this problem for you like that. The second problem, I'll use second fundamental theorem of calculus, and then I'll show you the other method if I have time here on this video. So second fundamental theorem of calculus says find f prime of x. Well, I'll take the derivative, and so that means I'm taking this side with respect to x, the derivative with respect to x. And what happens is those end up canceling each other out, and I plug in my x squared. The one complication with this problem is since it's not just a plain x, you've got to remember to take the derivative of it. So we'll have to multiply by 2x. And so my answer ends up being f prime of x equals 2 over x. Let's say you didn't recognize it. You can remember fundamental theorem of calculus. Every once in a while, you might still be able to do it without the fundamental theorem of calculus. So what I mean by that is we could have just integrated 1 over t and said, well, the integral of that is ln of absolute value of t. And then I could have plugged in 1 and x squared. So I've got ln of absolute value of x squared minus ln of 1. Well, this is equal to the f of x, by the way, the big F of x. So big F of x is actually equal to, this doesn't really need to be there, I have 2 ln of x, and then this would be minus 0. So when I take the derivative of this, I'd end up getting 2 over what's the derivative of ln of x, which is, it's 1 over x. So I end up getting the same answer. But it is much easier to just remember second fundamental theorem of calculus.